Let's look at a problem that we can solve, or we know how to solve. This is the integral of x times e to the x squared dx. So if you remember, when we talked about u substitution, we say that we make u the expression that after taking its derivative is sitting right there to cancel out. So if we let u here be x squared, then du dx is 2x, and this means that dx is equal to du over 2x. So this will let us rewrite everything in terms of u here. So this becomes x e to the u times du over 2x, which is equal to, we can cross out the two x's, factor out 1/2 e to the u du, and this is just going to give us 1/2 e to the u plus c. All right, so this is a problem that we know how to solve. Let's look at another problem. I'm going to call it problem 2. Integral x e to the x dx. Now we can say, oh, why not use u substitution? But u substitution may not work, because first of all, if we say let u be x, that doesn't change anything. We just end up with integral u e to the u du, which doesn't change the problem. If we say let u be e to the x, let's see what happens. We end up with du dx is equal to e to the x, so that dx is equal to du over e to the x. All right, what does this do? We can now say that our problem becomes xu times du e to the x, right? So how does that make things work out for us? That doesn't really work out, because we have xu du e to the x. So we end up with okay, let's just keep going. So we have integral, we have u times du, but now e to the x is u, so we can cancel things out, and we are left with x du. But then x, we can rewrite x as because here we said let u be natural log, let u be e to the x, so we can rewrite x as natural log of u, right? So we end up with maybe natural log of u du, but we don't know the integral of natural log of u yet. We don't. So u substitution doesn't help us for this particular problem. All right, what we can do is use a method called integration by part. So I'm just going to make a note, say we don't know how to do this yet. Okay, so enter integration by parts. So what does integration by parts means? Let's introduce it. Or when I say introduce it, let's actually derive it. Sometimes it's good to just derive something mathematically. So assuming we have two functions and we're looking for the derivative of their product. So we say d dx, we're looking for the derivative of two functions, u of x and then times v of x. Two functions, u of x and v of x. So if you remember from Calc 1, you can apply the product rule to get u of x times v prime of x, right? Plus v of x times u prime of x. Okay? So now, what we can do is we can integrate both sides. If you integrate both sides, what do you end up with? You integrate this side. Oh no, I need yellow. This side, you just get the inside because you have a function and you have the derivative of a function, sorry, the derivative of the product of two functions, and then you take the integral. That means you just get back the two functions. So that the left hand side gives us u of x, v of x. And then the right hand side, we have to worry about the integral. So we have integral u of x, v prime of x dx, plus the integral of v of x, u prime of x dx. Now, let's rearrange things. If I rearrange this, I will end up with, let's bring this one, this particular one, to the left hand side, and we end up with integral u of x, v prime of x is equal to, then let's bring the one on the left hand side, let's bring it to the right hand side. So we end up with negative u of x, v of x, right? Negative u of x, v of x, and then, sorry, this is going to be negative if I bring it there, negative right here. So plus integral v of x, u prime of x dx. Okay, but what I can do is I can just multiply it through by -1 to end up with u of x times, sorry, I don't have my dx here, and this is v prime dx, and this is equal to, all right, so if I multiply through by -1, I get u of x, v prime of x. So I'm just gonna make it remove the x so that it's a little bit more compact. So u of x, v of x dx, okay, is equal to u times v minus the integral of v u prime dx. All right, u v prime dx is equal to u times v minus integral v u prime dx. This is actually what, when we talk about integration by parts, this is the formula we end up using. And we're going to do some examples to see how we use this formula. It's a fun topic. I like this topic. So let's look at some examples. It's quite straightforward. Let's start with the first example we did. We want to find the integral of x e to the x dx. Okay. The first thing you do is you choose your u and you choose your dv. All right. So give me a minute. Let me I want to go back to the thing I put in the box. So I can rewrite this as, let's rewrite this as u, integral u. Instead of v prime dx, let's write it as dv is equal to u v, and then instead of in place of v prime dx, let's write that as du. Okay, it's the same thing. And if you want to know why we can do that, you can ask me in class. But it's quite easy to tell, to see. All right, so we're going to focus on this particular form of the formulation. We're going to use this. All right, so your integral that's given to you, you're going to assume that this integral, any integral that's given to you, is your integral u dv. So the first thing you want to do is, when you look at your integral, you want to choose which one is your u and which one is your dv. So in this case, I'm going to choose my u as x, and then I'm going to choose my dv as e to the x dx. All right, to go from u to du, so you want to find, you have your u. If you can find u and v, and then v and du, then, so if you can find, let me see, u and v and du, then you can just use the formula. But the good thing is that we already have u, we just need v, and then we need du. All right, so we have u. To go from u to dv, sorry, from u to du, we need to find derivative, the derivative of u. So du dx, which is derivative, du dx is equal to 1. So this means that dx or du is equal to dx. So from let's do this. From here, oh, what did I just do? From here to here is differentiation. You're looking for derivative. Now we want to find v. To find v, we take the integral of dv. So v is the integral of e to the x dx, which is just e to the x. Don't worry about the c in this particular context. All right, so what did we do? We went from dv to v, and this is integration. All right, now that we have our u, we have our u, we have our du, we have our v, we have our dv, which we don't need. We just need u, v, and du. So if we go back to our problem, our problem, which we're using this formula, remember, we're using this formula. Okay, so the formula, we need u is x, then we need v is e to the x, and then we need v du. All right, so we have minus v e to the x, du is dx. Okay, so this gives us x e to the x. We take the integral of e to the x, we just get e to the x plus c. All right, So integration by part has helped us solve the problem we couldn't solve with integration by substitution. Now, let's try a second problem. How about natural log of x dx? Remember, we converted this problem to natural log of x, and we still couldn't solve it. So let's see, how can we use integration by parts to do natural log of x? We're going to choose a u, and we're going to choose a dv. So I'm going to choose my u here, natural log of x. Then my dv, all that is left is dx. So if I take the derivative of natural log of x, that tells me that my du is just the derivative. My du becomes 1 over x dx, because du dx is 1 over x. And I'm going to move this a little bit. And dv is just the integral of dx. So v is the integral of dx, 1 dx. So v is just x. I hope this makes sense to you. So we come back to our problem. We use the formula for integration by part, which is uv. U is natural log of x. V is x, so u natural log of x times x minus the integral of v du of x times 1 over x dx. All right, so this becomes x natural log of x integral minus integral dx, because the two x's cancel out. All right, so we're left with x natural log of x, the integral of 1 dx is just x, and then you add your c. So that's integration by parts. Okay, let's try another problem. Problem 3. How about we look at the integral of t squared e to the t dt. So here you start wondering, how do we choose our u? I have a rule of thumb, right? The way you choose your u is you choose the function that after taking its derivative, it reduces. What do I mean by that? Its power reduces. I mean that its natural form as a polynomial reduces. So we chose u. We could have chosen e to the x as our u, but we chose u to be x. When you take the derivative of x, you just get 1. So it goes from a polynomial of degree 1 to a polynomial of degree 0. All right. Here, natural log of x is not quite a polynomial. But when you take its derivative, it reduces to something that looks like a polynomial, but it's not quite a polynomial. But its degree is way lower than that of a polynomial. It goes from natural log of x to x to the power of -1, which is the same thing as 1 over x. All right. So that should give us an insight here. If we choose e to the x or e to the t as our u in this case, then if we take its derivative, it doesn't reduce. It stays the same. It stays as e to the t. So I think we should try choosing u as t squared. All right. So that means that our dv in this case is just e to the t dt. So if we take the derivative of this du, du now becomes 2t dt, all right? And v becomes the integral of e to the t dt, which is just e to the t. So let's plug this into our formula for integration by parts. Again, the formula says u, maybe I should write it up here. So the formula, well, let me just write it here in green first. Formula says u v minus integral v du. So that's the formula we should be using. All right, so let's now do it in blue. So it's u t squared v e to the t minus the integral of v du e to the t times 2t dt. Okay, so we're getting somewhere. This is t squared e to the t. We can factor out the 2, so we have minus 2 t e to the t dt. So we factored out the 2 over here. This 2. Remember, constants are not troublesome things. You can push them around. So you factor out the t, and then I'll factor out the 2 and keep the t. You cannot factor out the t at all. All right. Now, what do we have? We have something that we're actually familiar with. Look at this. Look at this. This is t e to the t, right? Another way of writing it, or another way of thinking of this, is that it's the integral of x e to the x dx, all right? Okay? Which we have done already. We did this already. Okay? We did this. We did it right here. Oh. The integral, that's here. This. And we have the answer for it. X e to the x minus e to the x. So, what I'm pointing at is that we should go ahead to finish this problem. We have to go ahead and do this integral, and in fact we need to use integration by parts in doing the integral t e to the t dt. But we already have the answer already, because that was the first problem we solved. So this becomes t squared e to the t minus 2. The integral of e to the t e to the t dt is t e to the t then minus e to the t. Okay, and then we're gonna add a big C at the end. So this is the final solution. Okay, all right. I'm gonna give you one to try. Number 4. This is x cosine of x dx. All right. So if you do this right, I want you to try it. Try it before watching this, finishing this video. Just pause the video and try doing it. But your answer will be maybe pause it now and do it, and then check to see if you get this answer. X sine x. Are you paused? You should pause. But the answer is x sine x plus cosine x plus c. Try it. All right, let's do number 5. Let's try integral 1 to 0 inverse tangent of x, inverse tangent of x, arctan of x dx. Okay. Now, well, let's choose our u. Let's go with, it's okay to start with one u, and if it doesn't work out, go to another u. But let's start with inverse tangent of x, and then as our u, and then dv is dx. Okay. So this means that du dx, the derivative of the inverse tangent of x, is 1 over 1 plus x squared. So it's du dx is that, then du is just going to be that times dx, and v is actually just x. Okay? Now, what do we have? Well, let's move this a little bit farther away from where we are. So integration by parts says u, our solution should be u v minus integral v du. All right, so that means that this should be u is x. No, u is not x. U is inverse tangent of x. V is x minus integral v, which is x, times du, 1 over 1 plus x squared dx. Now, what we're going to do is we're going to actually take a look at the limits of integration that has been given to us. We're going to make sure we include those. So the limit of integration is, we're going from 0 to 1, and this is 0 to 1. So we're going to carry all this along. So before we evaluate the limit of the integral at the limits of integration, we have to first of all finish the second integral. And the second integral is an integral we actually can solve using integration by substitution. So here we're going to do another it's a u substitution. Maybe I should use the same u, maybe I should use a different kind of u. So I'm going to use a different kind of u, and I'm going to do it in a different color. So I'm going to say let u be 1 plus x squared. So I'm doing integration by substitution. So du dx is just 2x, so that dx is 2x over du. All right, so come back to our problem. This is x, inverse tan of x. We're going from 0 to 1 now. Then we have integral 0 to 1, but now we need to change our bounds of integration, because this 0 to 1 is for when we're dealing with x. Now we're dealing with u, so we have to change our bounds of integration, or our limits of integration, whichever term you want to use, from 1 to 2 actually, because you're just plugging 0 into u, and then plugging 1 into u. So if you plug 0 into u, you get 1, right? And you plug 1, you get 2, 1 plus 1 squared. And then put the x there. This is just 1 over u times 2x du. I screwed up here. So this should be Yes, this should be du over 2x. I probably said du over 2x and wrote something else. All right, so this is du over 2x. Then you can cancel this out and factor out the 1/2. We're getting somewhere. And then we're going to go from 0 to 1 minus 1/2 the integral 1 to 2 of 1 over u du. All right, so if you do that, this is x inverse tangent of x 0 to 1 minus 1/2. The integral of 1 over u is just the natural log of u. And our bounds of integration is in terms of u now. So what can we do? Or what should we do now? We should just plug in our numbers. When you plug 1 and 0 to the first term, you get just when you plug in 0, you get 0. So let's not worry about plugging in 0. Let's just plug in 1. We get 1 times inverse tangent of 1 minus, you plug in natural log of, plug in 2, plug in 1 into the natural log. So you're now left with so you get the inverse tangent of 1 means the angle whose tangent is 1, and that is pi over 2. And then the natural log of 1 is 0, so you just have pi over 2 minus 1/2 natural log of 2. So that's your final answer. Actually, sorry, I misspoke. The angle whose tangent is 1 is pi over 4. Pi over 4. Yes, so this is our final answer. All right, so I want you to try this, and then we can discuss it in class. Is the integral of e to the x sine of x dx. Now, let's discuss this a little bit. You have two functions that their derivatives do not reduce. What do I mean? If you have e to the x, if you take the derivative of e to the x, you get e to the x. If you have sine x, if you take the derivative of sine x, you get cosine x. And remember, cosine x and sine x have the same kind of behavior. They're sinusoidal. In fact, cosine x is just a shifted sine x. So if you think about it, if this is your sine function, right? Okay. Now, cosine function, if you move your vertical axis, if you move it here and keep this graph, you get your cosine function. Just move everything, move all your axes, move them like so just move your axis over here like this. All right, you get a cosine graph. You keep the same graph, it's the same graph. Sine graph and cosine graph are the same thing. So the two functions behave the same. They do not decay. The derivative doesn't decay. The derivatives are the same, have the exact same behavior as the function. So that makes it difficult here to see, to choose a u, but we have to choose a u. So I would encourage you to choose any u you feel like. So you can choose e to the x as a u and continue from there. But there's a trick that I would like to see how you manipulate with in this case. Okay, so try it, and then we can also try it in class. The answer I got when I tried it is I got negative 1/2 e to the x cosine of x plus 1/2 e to the x sine of x plus c. So I want you to check my answer because I might be wrong. All right. I will see you soon.